For section 5.3, the book actually starts getting into more of the short integration rules. We've been talking about the basic power rule for a couple of sections now, and a few of the problems. You'll start seeing it used in a lot more expanded form in this section. So just some rules that I want to remind you before we get started into some examples here. The integral of x to the n power with respect to x, all you're going to do every single time is add 1 to that exponent and then divide by that new exponent. So the integral of x to the n is x to the n plus 1 divided by n plus 1. And then we have to add the constant of integration. Now that integral power rule works for all cases except when the exponent is to the -1 power. Of course, when the exponent's to the -1 power, that's the same thing as 1 over x. Then you're supposed to remember from Calc 1, when you took derivatives, the derivative of the natural log of x was equal to 1 over x. Well, now we say that the integral of 1 over x is the natural log of the absolute value of x plus the constant of integration. Now you'll see in parentheses here, I put y the absolute value. Well, that absolute value really should be there in this case. And of course, we never had to do it in a Calc 1 class. If you think about whenever we take the derivative, when I say the derivative with respect to x of the natural log of x, and you say, well, that's equal to 1 over x. Why is there no absolute values in that problem? Nor should there be. Well, why? Because implied in the original domain restriction of the problem, you know you couldn't take the derivative with respect to x as something that didn't exist in the first place. So by the very fact that I'm asking you to take the derivative with respect to x of the natural log of x, automatically x is restricted to be positive values. It cannot be 0, it cannot be negative. So then whenever we take the derivative and say it's 1 over x, that's still implying that x is positive. We don't have to put it because it was already in the domain restriction of the original problem. But now down here, if our original problem is 1 over x, you know that the only domain restriction on that x is that x cannot equal 0. 1 over 0 does not exist. But 1 over x would exist no problem if x is negative or if x is positive. Well, the answer would not exist if x is negative. That's why we have to say it's the natural log of the absolute value of whatever that x is in order to make sure that the answer always exists. So please remember, whenever your answer is going to involve a natural log that you get from 1 over x dx, it has to have that absolute value around the argument inside the logarithm. Otherwise, it's going to be wrong. Up next, if you have the cosine of an angle kx plus b with respect to x, I need you to think back to what we did in Calc 1 with the chain rule. Whenever I said the derivative of any trigonometric function, you took the derivative of the trig function, you kept the angle, and then the chain rule said times the derivative of the angle. Well, this is the same idea. We're going to say the integral of any of any trigonometric function. You integrate the trig portion, keep the angle, and you divide by the derivative of whatever's on the inside of that angle. So in this case, if my angle is kx plus b, notice I'm dividing by k here. Now, this will always work. I call it the reverse chain rule. This reverse chain rule will always work as long as whatever interior argument you have is a linear function. If it's not linear, that reverse chain rule is going to fail miserably. So what's the integral of the cosine of kx squared plus b? I don't know. But I do know that the integral of kx plus b is going to be 1 over k sine of kx plus b plus c. And again, the trig part, you say, well, we know that the derivative of cosine would be negative sine. The integral of cosine is positive sine of that angle divided by the derivative of the angle plus your constant of integration. Well, when I say, well, what's the integral of the sine of kx plus b? You got to think, well, since I can take the derivative of a negative cosine and get a sine, the integral of sine is going to be negative cosine of that angle divided by the derivative of the angle, k, plus your constant of integration. Similarly, with any exponential function, if I have e to the kx plus b power, I can say, well, the derivative of any exponential function is that exponential function times the derivative of its exponent. The integral of any exponential function is also that exponential function, but now we divide by the derivative of its exponent. And again, this reverse chain rule is going to apply every single time the interior function, the function inside of the function, is going to be a linear. If it's not linear, like if this were e to the kx squared plus b, we're going to have to use some other technique. It doesn't satisfy the normal reverse chain rule. But in this case, we're looking at the ones that are more straightforward in this section. So we can say the integral of e to the kx plus b is 1 over k, e to the kx plus b, plus your constant of integration. Now, if I just said, hey, think about some things that we are used to or should be used to from Calc 1, if I say, figure out what the integral of secant squared x with respect to x is. Well, we should know that. We know that the integral of secant squared x with respect to x is the tangent function. How do we know that? Because we remember from Calc 1 that the derivative of tangent is secant squared. So whenever you see this, it's like you're playing Jeopardy with Calc 1 questions, and you say, what could I take the derivative of and get a secant squared? Since the derivative of tangent is secant squared, then the integral of this would be the tangent of x, of course, plus our constant of integration. If I have 1 over 1 plus x squared, you're supposed to be thinking back, what in Calc 1 did I take the derivative of to get 1 over 1 plus x squared? And you said, well, that was our inverse tangent of x. So we can say, since the derivative of inverse tangent of x is 1 over 1 plus x squared, then the integral of 1 over 1 plus x squared is inverse tangent of x plus the constant of integration. Similarly, we should be familiar with what we took the derivative of to get an answer of 1 over the square root of 1 minus x squared. Well, that was the derivative of my inverse secant function, so the integral of 1 over the square root of 1 minus x squared is simply, I think I might have said inverse secant, I meant inverse sine of x plus your constant of integration. Okay, now, the problems I want to look at with you here below, and there's several of them. Let's work our way through those. The first one here, number 8, and I have them listed on here too, so I think I'll just cover this up for now. For number 8, it's giving me the integral of 8 over s to the 4th power, and I'm asking you to integrate that with respect to s. So I can say, well, no problem. The integral of 8 over s to the 4th with respect to s, notice the first thing I did is I went ahead and wrote the s to the negative 4 power, and then that enables me to do the power rule a little bit more easily. I add 1 to the exponent, divide by that new exponent, plus the constant of integration. This answer is good, it's just in sloppy format. You always want your answer to be back in the original form, so I want it back in a rational expression with positive exponents. So I can say, well, then this is going to be 8 over, and I could leave the negative in the denominator. I prefer to put it in the numerator. So I said negative 8 over 3, and then I'll have s cubed down in the denominator. Please remember that 8 is not tied to the location of s to the negative 3. Sometimes students, unfortunately, whenever they move the s down to the denominator, think that they need to move the 8 with it. 8 is understood to be to the 1st power. It does not move. So we get negative 8 over 3s cubed plus c for our final answer. Our next one, we have the integral of 3 separate terms. We can go ahead and integrate each term individually. So I can say power rule on the first one, I would get 5x to the 4th over 4. Power rule on the second one, x to the negative 2 becomes x to the negative 1. We divide by that new exponent, still keeping the minus sign out in front for now, minus power rule on the next one, we'd say x to the 3/5, and whenever I'm doing that, I'd say, well, x to the 3/5, I'm going to have to add 1 to that exponent. This one's not going to be good. I'm going to have to correct that. And oh, I meant to put a negative 3/5 in my original problem. Let me fix that. So if I have x to the negative 3/5, then when I add 1 to the exponent, negative 3/5 plus 1 is x to the 2/5. I divide by that new exponent plus my constant of integration. Now, I go down and I try to simplify that, and I'll say, well, my first term doesn't really simplify. It'll just be 5x to the 4th over 4. The second term, I'm subtracting a negative, so I might as well add. And I know that the x belongs in the denominator. That is much better written as plus 1 over x. And then my last term, if I'm dividing by 2/5, I'm multiplying by 5 over 2. So I get 5 over 2 x to the 2/5 plus the constant of integration. For your next term here, you have, or the next problem, the integral of 1 over the root of x with respect to x. So I can say, well, okay, if I'm trying to find that integral, I'll just go ahead and say 1 over the square root of x. That's the same thing as x to the negative 1/2 power. And it's important to go ahead and simplify it to that to make the power rule easier to do. So once I've done that, then I can just say, well, all right, now when I integrate, I add 1 to the exponent to get x to the 1/2, divide by that new exponent of 1/2. And you know, if you divide by 1/2, you're multiplying by 2 over 1. So I just get a final answer of 2 on the square root of x, x to the 1/2 square root of x, plus your constant of integration. The next one here, this is where I need you to think about anytime you have a linear function raised to a power, this is the reverse chain rule. So you can say, all right, if I have a group to a power and I take the derivative says bring that power down in front, multiply it, times the group raised to the 1 less power times the derivative of the inside. Well, whenever you integrate, you're going to say, let's take that group to the 1 higher power, so the negative 3 power becomes the negative 2 power. We divide by that new power, and we divide by the derivative of whatever's inside of that group, which is where that 4 in the denominator came from. Now, if I'm trying to simplify this, of course, I add my constant integration. When I try to simplify, I'd have a factor of negative 8 in the denominator. So then I can say, well, that factor of negative 8 in the denominator, I'll leave as an 8 in the denominator. I meant to put a negative in my numerator here. That needs to be there. So negative 1 over 8. And then the 4t minus 9 to the second power, I put that in the denominator, plus your constant of integration. For my next one here, if I have the integral of x squared plus 2x minus 3 over x to the 4th. One thing that's extremely important for you to understand whenever we're trying to integrate this problem is that there is no such thing as the integral quotient rule or the integral product rule. What you're going to have to do is any algebra that can be done to simplify, you must do before you integrate. So I need to understand that when I have 3 terms all divided by 1 term, this division of x to the 4th distributes into each term in the numerator. When it goes into the first term, x squared over x to the 4th gives me x to the negative 2. 2x over x to the 4th is just going to give me 2x to the negative 3. And then minus 3 over x to the 4th minus 3x to the negative 4. This enables me to set up the problem to where now I can do the power rule pretty easily for each one of them. The first one, you'd say, if I add 1 to that exponent, it's going to become x to the negative 1. Then I divide by that new exponent. The second one, when you add 1 to the exponent, you're going to get 2x to the negative 2. Divide by that new exponent of negative 2. The next one, minus 3x to the negative 3, when you add 1 to the exponent, divide by negative 3, plus our constant of integration. Always have to have that. Now, when we simplify each term, the first one, I would rather you just go ahead and say that's the same thing as negative 1 over x, since that x was to a negative exponent. The second term is going to be minus, since it's plus a negative. The 2's cancel. The x squared goes to the denominator, so it should be plus 1 over, minus 1 over x squared, plus a negative is minus 1 over x squared. Then the next one will be plus because you're subtracting a negative. So I get plus, the 3's cancel, the x cubed goes to the denominator, plus 1 over x cubed, plus our constant integration. Nice final answer there. For the next one here, number 6, we have the integral of the sine of 9x with respect to x. Well, we think, okay, we know that the integral of the sine function is going to be the negative of the cosine function, because you're thinking, what can I take the derivative of and get a sine? Derivative of negative cosine is sine. So the integral of positive sine is negative cosine. You keep the angle, then you divide by the derivative of that angle. So I'm dividing by 9 in the denominator, plus your constant integration. That's a fine answer right there. It might look a little bit better to go ahead and put that out as a coefficient, call it negative 1/9 cosine of 9x plus c. For my next problem here, we have the integral of 4 theta plus the cosine of 8 theta, and then we're integrating this with respect to theta. Okay, I like to throw in theta every now and then just because it gives students trouble. They're like, oh no, what do I do? Remember, it's just a variable. You can think of that as x if you prefer. You're integrating with respect to theta, so it's your variable, and you said, well, okay, I'm going to increase the power by 1. It's going to become 4 theta squared over 2. That's where the 2 theta squared comes from. Then you have to integrate the cosine of 8 theta. So you can say, since the derivative of sine is cosine, the integral of cosine is sine, I'll get the sine of 8 theta divided by the derivative of the angle 8 plus c. And I'll just leave that as my final answer. Perfectly fine. For the next one here, number 8, we have the integral of 2x plus e to the 14 minus 2x power with respect to x. So you could say for this one, the first term, whenever you're integrating it, it's just polynomial. It's just a polynomial, so you'll use your power rule. 2x becomes 2x to the second over 2. That's why we just get x to the second. Excuse me. Now for the second one, remember, that's not a power rule. That's an exponential function. You're supposed to remember the integral of any exponential function is that exponential function divided by the derivative of its linear exponent. So since my exponent was linear, I can just look at the derivative of that and say, well, the derivative would be -2. Then I need to divide by -2. Had that been any other power of x, you could not take the derivative in this manner. But now I can just say, well, for this problem, it was pretty easy. It was x squared plus e to the 14 minus 2x all over -2 plus your constant of integration. I cleaned that up a bit and just said, well, if you're dividing by -2, then that's going to make that second term minus 1/2 e to the 14 minus 2x. And then, of course, we have our plus the constant of integration. For the next problem here, you might recall something I said earlier is that if there's any algebra to be done throughout the problem, you must do that algebra first. I was referring to that in number 5, where you had a quotient. I said there's no such thing as the integral quotient rule. You have to distribute the division before you can integrate. Same thing in number 9. Looks like you have a product. Well, you don't have an integral product rule. So I have to distribute out those two binomials in this problem before I start trying to do the calculus and the integration in it. So I distributed an x through that second group to get the 3x cubed minus 5x squared. I distributed an x to the -1 to get the 3x and the minus 5. Now, whenever I integrate it term by term, the first one's going to become 3x to the 4th over 4. The second term, minus 5x cubed over 3. The next term, plus 3x to the second over 2, and then minus 5x to the first, and you don't need to divide by 1, plus your constant of integration. Done. Now, for the next one, again, I'm asking you to recall your Calc 1 derivatives. You say, what could I take the derivative of and get a secant tangent? You say, well, I know that the derivative of secant is secant tangent. So the integral of something involving a secant tangent has to be a secant, and you never ever mess with the angle. So the angle is still 3x, but then you say, yes, But just like when I would take the derivative, I would have to multiply by the derivative of the angle. Now when I'm integrating, I have to divide by the derivative of the angle. So you say, well, yes, the integral of secant 3x tangent 3x is secant 3x, but then you have to divide by the derivative of the angle, 3. That's where the 1/3 out in front came from. And then as always, you put plus your constant of integration. Few more through here. Number 11 asks us to integrate similar to the last one where we had secant tangent. This time I'm putting a cosecant cotangent. So you're supposed to remember from your derivative knowledge, what can I take the derivative of and get a cosecant cotangent? You'd say, well, I know that the derivative of cosecant is negative cosecant cotangent. So the integral of a positive cosecant cotangent would have to be a negative cosecant of that angle. Where did the 1/5 come from? Because you always have to divide by whatever the derivative of the angle is. So I would have said negative cosecant of 5z all over 5. That's where the negative 1/5 cosecant of 5z plus your constant of integration comes from. Now we're to some problems where we have to do a little bit more thought. So for number 12 here, I said I want to solve the differential equation with a given initial condition. So I'm telling you that the first derivative is equal to secant squared of 3x. And I'm telling you an initial condition on the original function. I'm saying that the original function evaluated at pi over 4 is equal to 2. That's just information to be able to get rid of c. So notice what I did here. I said, oh, all right, my first derivative is the secant squared of 3x. Whenever we integrate that, we know that the original function is going to be the integral of secant squared is tangent. Since the derivative of tangent is secant squared, I keep the angle. But then I have to say divided by the derivative of that angle. So I'm getting 1/3 the tangent of 3x plus the constant of integration. Now, I told you that the original function evaluated at pi over 4 was 2. That's information to get rid of that value of c. So I plug pi over 4 into my answer. 1/3 times the tangent of 3 times pi over 4 gives me tangent of 3 pi over 4 plus c is 2. Now, the tangent of 3 pi over 4, that's going to split quadrant 2. At that point, the tangent is -1. So you have 1/3 times -1 plus c is equal to 2. When I add 1/3 to both sides, this is the same thing as 6 over 3. 6 over 3 plus 1 over 3 is 7 over 3. I can see that the constant of integration is 7 over 3. So then my answer, I already knew that the variable part of the answer was 1/3 tangent of 3x. Now I've been able to solve, given the original condition, that c has to be 7/3. So I have a very specific answer for my original, as opposed to the general answer with the c in there. So 1/3 tangent of 3x plus 7/3. Gorgeous. Now, I know what you're thinking. You're thinking, well, we need to be able to do that with multiple levels of the derivative. Yes, that's what I did in 13. So notice this time, I'm giving you the second derivative is equal to t minus the cosine of t. And I'm giving you information about the first derivative and the original function. So this is going to enable us to take the antiderivative or the integral twice to get back to the original function and solve for c in each time we integrate. Here's what I do when I try to solve out this problem. I'm given the second derivative and these two are original conditions. When I try to integrate, I know that the integral of t is just going to be t to the second over 2, or 1/2 t to the second. The integral of a negative cosine is going to be a negative sine. So then I can say, well, all right, the integral of cosine negative sine, I have plus my constant of integration. I need to solve for what that value of c is before trying to worry about what the original function is. So I plug in what I know. I know f prime of 0 is supposed to be 2. Well, if I plug a 0 into f prime of x, it's just going to be 0 minus 0. So 0 plus c is equal to 2. This allows me to see that this constant of integration is 2. So now I can conclude that my exact first derivative is 1/2 t to the second minus the sine of t plus 2. From that, though, I need to worry about the original function. And please keep in mind, I had to get the specific first derivative with the value of c solved for before worrying about what the original function was. So now I'm going to try to take the integral one more time. The integral of 1/2 t to the second is going to become 1/2 t to the third over 3, 1/6 t cubed. The integral of the negative sign is a positive cosine. Since you can take the derivative of cosine and get negative sign, the integral of negative sign is positive cosine. The integral of 2t to the 0 is 2t to the first plus your constant of integration. Now, once again, we need to solve for that constant of integration. We know that the original function evaluated at 0 is supposed to be -2. So if you plug a 0 into this function, the first and third term would become a 0, but the cosine of 0 is 1. So f of 0 is going to give me 1 plus c, and I know that 1 plus c has to equal -2. Well, if I subtract 1 on each side, I'll see that the constant integration is -3 here. So then I can plug that -3 into my function and get my original function that satisfies this second derivative and all criteria given in the original conditions is 1/6 t cubed plus the cosine of t plus 2t minus 3. Now, these next few application problems, I'll go ahead and talk about them here. You will not see any problems like this in the assignment for this section yet. They'll come up later in applications. They used to be introduced in this section, so I kind of like to keep them with this section. It really doesn't involve too much more information. So, but now do keep in mind that you won't see assigned problems like 14 through 17, and I have a typo in 17. There's 17p, that should just be 17. So looking at these here, number 14. And again, if you struggle with these, you won't see anything in the homework like them, but they are gorgeous problems. A ball is thrown upward with a speed of 48 feet per second from the edge of a cliff, 432 feet above the ground. A second later, another ball is thrown upward with a speed of 24 feet per second. My question is, do the balls ever pass each other? So do the balls have the exact same height at some moment in time? In order to think about this question, what I did is I went ahead and created two separate time functions. I'm going to have the path of ball one. Now, what did you know about ball one? Ball one is thrown upward at a rate of 48 feet per second, and it's thrown upward a second earlier than the second ball. So I'm saying we know the acceleration in this problem is just acceleration due to gravity. And throughout this textbook, it's going to use the -32 feet per square second for the acceleration due to gravity. If you're in a physics class, you probably are a little bit more precise and use 32.2. I'll be with what Rogowski wants in this class, and it will also match what Achieve is wanting on their answers and just stick with a -32. So my acceleration function is -32 feet per second every second. When I integrate that backwards to get to velocity, I'm integrating with respect to time. So -32t to the 0 becomes -32t to the first plus the constant of integration. Now that constant of integration, it's the same thing as the original velocity. So you know that the velocity at 0 is 48. So that allows you to see that the constant of integration is just 48 here. So then we can say, well, then my velocity function for this first ball is going to be -32t plus 48. Now, when I try to integrate again to get backwards to the position function, once again, we're integrating with respect to time. So -32t to the first becomes -16t to the second. 48 becomes 48t. And then you would say plus c, where c is your original position. And your original position, well, where was it at time 0? It was at 432 feet above the ground. So that's why I put S of 0 there. That's at 432. Now, for ball 2, in this one, you might accidentally make the conclusion, oh, c is always whatever your original velocity or original position is. That's true, but you have to be a little careful with that. Here's what I mean. For the second ball, I can say, again, the only action for acceleration acting on it is gravity. Gravity is going to pull it down at a continual rate of 32 feet per second every second. When I integrate that to get to my velocity function, similarly, I'm just getting negative 32t plus c. But now, here's the trick. How do I solve for that value of c? Unlike before, I can't just simply say, well, let's just plug 48 in for c. You might think, well, can I just plug a 24 in for c? No, you can't, because if you plug a 24 in for c there, you're saying its velocity at time 0 was 24. That's not true. This ball was released 1 second later, so you can say the velocity at 1 second is 24. Now use that to solve for what c is equal to. So I get negative 32 times 1 plus c is equal to 24. Negative 32 plus c is 24. It's going to give me that this constant of integration is 56. So the velocity function for the path of the second ball is negative 32t plus 56. Then I can integrate that to get to the position function for the second ball. And I can say, well, okay, that's going to give me negative 16t squared. And then I'll have plus the 56t when I integrate, plus the constant of integration. Now, once again, I need to be wary with that constant of integration. I can't just plug 432 in for it, because I know that the position 1 second later, it was still at 432 feet because it was released a second later. So I had to say the position at 1 second was 432. Plug a 1 in for t. You'll get negative 16 plus 56 plus c is equal to 432. That's going to give me 40 plus c is 432. Subtract 40 on each side. You'll get the constant integration is 392. So now I have my position function for the first ball, position function for the second ball. In order to answer the question, do the balls ever cross paths, just set your two position functions equal to one another. When you do that, you see that a lot of stuff cancels out. And I forgot to put the t squared in this second one. There's a t squared right there. Doesn't really matter because it cancels out on both sides anyway. And then the 56t minus 48t gave me a total of 8t on the right-hand side. And then the 432 minus 392 gave me a 40 on the left-hand side. So this is 8t is equal to 40. Divide by 8, we get 5. Now, time in this problem, I'm measuring it as the time after the first ball has been released. So when I get t equals 5, that's telling me that the balls are going to cross paths or be at the exact same height 5 seconds after the first ball is released, or you could say, or 4 seconds after the second ball is released. Okay, now that's a pretty cool problem. Looking on to some others, usually I ask a question on a test like this next one. Again, it's not going to be on your homework assignment for now. Some later sections will deal with problems like this. A stone was dropped off of a cliff and hit the ground with a speed of 120 feet per second. I'm asking you, what is the height of the cliff? Okay, so in order to answer that question, just like my last problem, the only acceleration acting on this stone is the acceleration due to gravity. This problem's measured in feet per second, so we can say, well, gravity's pulling it down at a rate of 32 feet per second every second. The velocity function, when I integrate that, I'll get to negative 32t to the first. And then you might say, well, why didn't you put plus c? Well, because I knew that the plus c would just be my original velocity. And I knew that the original velocity was 0 because of the keyword dropped. It wasn't thrown at any rate. It was just dropped off of the edge of the cliff. Because of that just dropping off the edge, its original velocity was 0. So I can say, okay, since I know that, then my velocity function is just very simple. And then I can go ahead and solve for the position function and say, well, the position function is going to be negative 32t to the second plus c, where c is just going to be your original position. We don't know the original position. The original position is what the height of the cliff is. So the goal of the problem is to solve for what that s sub 0 is. Now, here's the logic that I'm using. I know that it said that it hit the ground with a speed of 120 feet per second. So you know if it's hitting the ground at that, it's moving downward as it's hitting the ground. So that speed of 120 feet per second, that's a negative 120. So you'll see here where I set my velocity function. Since I know it hits the ground with a velocity of 120 feet per second, I set my velocity function equal to that. When I divide by negative 32 on each side, it's showing me that it took 3.75 seconds in order to hit the ground. That's the time of impact. How does that help? Well, that helps because I also know if that's the point at which it hits the ground, I know if I plug that time into my position function, I should get a 0. So S of 3.75 gives me negative 16 times 3.75 squared, plus that original position, which is the height of the cliff, which is what we're solving for. Gorgeous. When I calculated this out, I got the negative 225 feet plus S sub 0 is 0, which tells us that the original height of the cliff had to be 225 feet in the air. Very nice problem. Up next, we have 16, it's saying a car is traveling 50 miles per hour when the brakes are fully applied, produces a constant deceleration of 22 feet per square second. What is the distance traveled before the car comes to a stop? Nice problem. So this time, for once, we have a different acceleration function. So I know that my acceleration function, it's a deceleration, it's the car's brakes are producing a constant deceleration of 22 feet per second. So notice I said the acceleration is negative 22 feet per square second. Well, the velocity function, it's the integral of that, negative 22 times t to the first, plus it would be the original velocity. Well, and then I had to put the original velocity into terms that I could work with in this problem. Since the acceleration was given in feet per square second, I needed the velocity in feet per second. I was given the velocity in miles per hour. So up here, you'll see where I converted that original velocity in miles per hour to feet per second. I just said, well, I need to get rid of miles and I need to get rid of hours. So I need to multiply by hours, and I know that I need to divide by the equivalent of an hour. 60 minutes in an hour, 60 seconds in a minute, 60 times 60, 3,600. So I multiply by 1 hour over 3,600 seconds. And then in order to get rid of mile, I need to divide by 1 mile and multiply by its equivalency in terms of feet, namely 5,280 feet. So I just multiply, and you could just say, well, take your 50, multiply it by 5,280 over 3,600, reduce down that fraction. And I would prefer if you keep it in fractional form. It looks nicer than any sloppy decimal there. So 220 over 3 feet per second. Now I can say, all right, if that's my original velocity, then that goes into my velocity function. The integral of acceleration is negative 22t to the first plus the original velocity in terms of feet per second. Okay, now the position function, it's asking how long is the car going to go before it comes to a stop. So I need a position function. Position is going to be the integral of velocity, negative 11t to the second plus 220 over 3t to the first. Now, you could say plus c, where c is your original position, but if we allow our original position to be 0, then whatever s is evaluated at a certain time frame, that's going to be your stopping distance. So I purposely want to allow s sub 0 to be 0 here. Now, and I did the same thing in the next problem. You'll see I let s sub 0 equal 0 there as well. Now, we know that the car is going to come to a stop when the velocity function is 0. So you just set your velocity function negative 22t plus 220 over 3 equal to 0. And that's going to give you t is equal to 220 over 3 divided by 22, and then that reduced down to 10/3 of a second. So 3 1/3 of a second is going to take it to come to a stop. So this stopping distance, how many feet did it travel before it came to a stop if it took 10/3 of a second? You plug that into your position function. Negative 11 times 10/3 squared plus 220 over 3 times 10/3. Put that into your calculator and you'll get 122.2 repeating. For a final answer, it's probably better to have the non-fractional answer so you can see it's just a little bit more than 122 feet. But I did put the line over that to be that's still a precise answer. So this would be 122 and 2/9 or 0.2 repeating feet. That's a decent stopping time, although since the car was just going 50 miles per hour, that's really not that decent. Maybe it's like a school bus or something like that. For number 17 here, says, once again, you're going to have a car braking. A car braked with a constant deceleration of 16 feet per square second. It's producing skid marks measuring 200 feet before coming to a stop. How fast was the car traveling when the brakes were first applied? So this time we're trying to solve for what the original velocity was. So I'll say, okay, think about what I know in the problem. I know it said that the car brakes with a constant deceleration of 16 feet per second. That's where that came from. I do not know the original velocity. So I can say my velocity equation is just going to be negative 16 times t, the integral of acceleration, plus whatever that original velocity is. Now, I know that the car is going to stop when the velocity equation is equal to 0. So then I can say, well, let's use that to our advantage since we know that. So I set the velocity function equal to 0, and now I solve for v sub 0. I can say it's going to come to a stop when v sub 0 is equal to 16 times t, and then t is going to equal v sub 0 divided by 16. So that's the time at which it's going to come to a stop whenever the time is equal to the original velocity divided by 16. And that should make sense. You're slowing down by 16 feet per second. So if you're slowing down by 16 feet per second, how many seconds is it going to take? However fast you're going divided by 16 is going to be the amount of seconds it takes to come to a stop. But now I'm going to take that and let's plug that into my position function. My position function would be negative 16t integrated to negative 8t to the second plus v sub 0 times t plus c, which would be your original position. And once again, I'm letting the original position be 0. So then I can say, all right, then if I want to find out how fast I was traveling at the beginning of this, I know it tells me that it took the car 200 feet before it came to a stop. So that's a very long stopping distance. So it took the car 200 feet to come to a stop. So the stopping distance was 200 feet. My displacement, 200 feet. I set my position or my displacement function equal to that. And I can say, well, I'll have my negative 8. And notice I already know, and the reason I did this is my position function, but it's a position function in terms of two variables, t and v sub 0. So I'm trying to solve for what the original velocity is in this problem. So I'm plugging what I know t is equal to from previous step into this position function. So instead of negative 8t squared, I say negative 8 times v sub 0 over 16 quantity squared plus v sub 0 times t, which is v sub 0 over 16, set that equal to 200. On the left-hand side now, you could say, well, if this is going to be negative 8 and you're dividing by 16 squared, I just went ahead and reduced that down to, I know 8 reduces with one of the 16s and gives me a 2. 2 times 16 is 32. That's going to be negative 1 over 32 v sub 0 squared plus v sub 0 squared over 16, or 1/16 v sub 0. That's equal to 200. It's easy to combine the left-hand side now because I know this is the same thing as 2 over 32. Negative 1 over 32 plus 2 over 32 gives me 1 over 32 times v sub 0 squared is equal to 200. Multiply by 32 on each side, I get v sub 0 squared is equal to 6,400. Take the square root of both sides, we get v sub 0 is 80 feet per second. Now, if you wanted that speed, and I don't know if I specified that it needed to be in miles per hour, I didn't, but I did it just for fun. If you wanted to know 80 feet per second into miles per hour, then in order to get rid of feet per second, you need to multiply by miles per hour. We know that for every 1 mile, there's 5,280 feet. The feet would cancel. For every hour, there's 3,600 seconds. The seconds would cancel out and we'll be left with miles per hour. So you just take your 80 and you multiply by 3,600 over 5,280, and that reduced down to 54.54 repeating miles per hour. Pretty cool problem. Now, I do think you'll see that the problems in this section, they'll go up to about where I stopped at 13. You really won't have too many of the application problems at this point, just because we don't have a lot of integration skills to work many interesting applications at this point. I just wanted to go ahead and discuss some with you because they will be seen in later sections anyway. I hope this helps out. Let me know if you have any questions, and please get to the Achieve assignment as soon as you can.